Hello mathematicians, we're now going to have a look at conjugates. I've mentioned these already, so if z equals x plus iy, then its complex conjugate is x minus iy. But there are some properties which it's good to have in the back of our mind, and we also need to know how to prove these properties. So the first property is that the product of the conjugate, or the complex number and its conjugate, is a real, which is x squared plus y squared. And the proof of that is that z bar is the product of a difference of squares. We combine our difference of squares and we get x squared plus y squared as a result, which is totally real. We'll see also later on that that has another significance. So this z bar product is important. Z plus z bar equaling, again, purely a real number, which is 2x, and you can see the proof here is pretty straightforward. Similarly, for the difference between a complex number and its conjugate, the proof is straightforward and it shows that what we get is a totally imaginary number. For the next few, the proof is not so easy, but the concept is quite okay. So the conjugate of a sum is the sum of its conjugates, and the proof down here, I'll just quickly go through it. So the conjugate of z1 plus z2, so we look at what z1 plus z2 is and we take its conjugate, which means that we just gather together the reals, the imaginaries, and we change the sign. And then once we gather those together, we can see that x minus iy1 is the conjugate of z1, and likewise for z2. This next property, the conjugate of a product is the product of its conjugates, is also not unexpected. The proof, so the conjugate of z1, z2 is the conjugate of that. We multiply those brackets out. We haven't yet taken the conjugate, which is why that line's up above. We change the sign here, which is what's changing the conjugate, which is what's giving us the conjugate. And then we go the other way in this proof in terms of simplicity. We look at what the product of the conjugates is. So we multiply that out and we see that we get the same thing here as we had there. Therefore, that property is proven. Now similarly, our last proof is horrible, but the concept is simple. So the conjugate of a quotient is the quotient of the conjugates. So when we look at this, here's our quotient. We're going to work on the quotient to realise the denominator. This is the quotient with the denominator realised. We change the sign between the real and the imaginary part. And this is therefore the left-hand side. Go to the right-hand side, work it. So realise the denominator. What we gather together is the same as we had up here, so we've proven the property. Could now go to set 1 and finish off 5 to 11.